Thank you, Andrew. But welcome to the I think this is edition 126 Zoom Rock Room. And we have our co-host Melanie back in tonight. She was on vacation last time from the Zoom Rock Room anyway. She was
Yep.
having some other fun with some other people. So how are you? How's your life been going, Mel?
Life has been pretty good, trying to enjoy all of this beginning of summer weather, some warmer weather.
I don't want too hot, too fast.
Right. If it stays like this, I'd be pretty good. I'd be content.
Yep. Yep. So lots have been going on in the last couple of weeks. So we'll get to a couple of those things here in a minute, but we're going to start the introduction because we got things to do here before we get our speaker in here tonight. So Melanie's going to start us out tonight.
Alrighty, as always, thank you guys for joining us every other week here on the Zoom Rock Room. My name is Melanie Tracy, and I am co-hosting here with Jerry Jones, our host of this program. I believe you said the number, Jerry, already, but I missed it. 26th episode of this program, and we thank you all for being here. As always, we are sponsored by Lair Architecture in Lake Havasu City, Arizona. Designing for the future is their motto. They have been our sponsor since the very beginning, so feel free. We give them a shout out every episode, and feel free to reach out to them. Say hello. See what they're up to out there. Alrighty, the Dirt Man Report. These are some of my favorite videos ever. The Dirt Man Report proudly supports the Zoom Rock Room, so we appreciate your support, Andrew. All of these videos that he creates are both educational and rather entertaining. I enjoy them myself. They are bringing geology to you is their motto. You can find them on social media platforms, including YouTube. If you have missed any of his episodes, any videos that you would like to rewatch, you can find them on YouTube. Like I said, if you want to learn more, you can follow Andrew Rockhound on any of the socials, Facebook, Instagram, TikTok, all of those platforms. His videos, like I said, are terrific. They are some of my favorites. He does a very good job.
And we have one tonight for Andrew to share. So
Yeah.
Perfect.
I'm going to stop sharing. Let Andrew take over here now.
Cool. All right, everybody. If you're following me on Facebook, if you're not, please do. You can get in on the 1,000 followers giveaway. So get in on that. But if you haven't been following me, you may not know about the fossil class that I did over the weekend. I've been involved with the Vernal School Educational Environmental Partnership, and I'm a partner in that. And we've been trying to get stuff going at the Montour Preserve, and the Montour Preserve fossil pit is there and open for everyone at any time. So we're just trying to get some education out there for people. It turned out to be raining on Saturday, but things still went great. So here's a little recap of that with my Dirt Man report for this evening. Give me 1 second so I can share it here. All right, everybody. And here we go.
Without further ado, here is Andrew Rockhound.
Dirtman here with a packed house at the Montour Preserve, and we are going to talk about fossils. This is going to be an amazing day. It's raining outside, but we are going to have a lot of fun, everybody. Thank you all for coming out. 400 million years ago, this is where the Susquehanna River starts. The Susquehanna River is actually one of the 5 oldest rivers in the world.
Today,
I am here to teach the very first Vernal School fossil class at the Montour Preserve, and it is an honor to share this knowledge with so many amazing people who are eager to learn. Thank you all. I'm Sean We just wrapped up the class back at the Nature Center and we're moving out to the pit. Everyone's already here. Look how many people are out digging. I'm gonna walk around, see what they're finding, help them out a little bit. This is cool. See this line of people here? That's really where to dig. They should be able to find some good specimens along that line. What do you think, Doug?
I think it's a good day.
Oh yeah.
Absolutely.
Great day at the Montour Preserve.
Yeah, awesome.
Oh yeah.
Nothing like hunting fossils.
Oh yeah, yeah. I'm here with Paisley and she just found a trilobite. First one of the day, here we go. Look at this, everybody. Right there, that's a tail. And it's kind of sticking out of that rock there. Great job.
Thank you.
So I'm here with John Zaktansky, the Middle Susquehanna River Keeper, and I have made up some STEM kits for use here at the Vernal School and the Susquehanna Association. Check that out. They're labeled in there. You just kind of dump them out and teach them the names and have them sort it the way it's supposed to be.
Pretty awesome. Thanks a lot. This is amazing. Very cool.
Not a problem. They basically gave me bins and bins of fossils to go through and determine what they were. So I've been coming up with different ways to utilize those for the kids here. So this is just one of the first that I've come up with, and hoping to come up with a lot more.
Well, they'll definitely get used. This is awesome. So,
Awesome.
very cool.
So I'm here with Bruno and Secrets, and I am going to give Bruno amazing bag of trilobites. There are 4 trilobites in here. There are tails, there's heads. Here you go. Bruno,
Thank you so
this is
much.
yours. She wheeled him from the Nature Center all the way to the pit. That is a feat that I don't know if I could even do. You are amazing. So I had to come over here and film with her. Absolutely amazing, your dedication to enjoy this with all of us. Thank you for being here.
Oh, thank you. Yes, I always like to bring my kids to learn everything around and explore.
Awesome,
Thank you.
awesome.
Invite us.
Awesome. Oh yeah, this is a nice Pygidium right there. Look at that. Very good job. She found it?
Yeah.
Great job. Give me a high five. Oh yeah. Keep on looking. You're all wet and you're muddy.
Thank you.
So many kids are coming up to me asking for identification.
Are these like the same by the pen? Can we use them?
As long as you put it back.
Okay.
You have to put it back. That's my hammer.
Well, they're weapons today.
Yep, there's a brachypod on there.
It's definitely something because
Yeah?
I'm all found it.
Awesome.
All right, I am here with Scott. Check that out. Look at that. That whole thing is still in the ground right there. That is in that rock. He is trying to pull it out, but that's the mold right there. Scott's got a challenge now. You got to get that out of the bedrock. That is a great specimen.
Because of marriage, I call 50% of that find.
You just got to find yourself something better, right? You got to show him up.
Found him.
Oh yeah, you found him. And he can find the rocks. I'm here with Ava, Michelle, and Emma, and they just pulled out both sides. This is actually the tail fins of a trilobite, and these are the ones that you never find. Amazing find. Great job, everybody. That is very cool. This has been an amazing event today. I'm so honored to be a part of the Vernal School Educational Partnership as a partner. And I would love to thank the Montour Preserve and Central PA Rock and Mineral Club. This is awesome. We had 150 people sign up. Over 80 showed up in the rain to come do fossils. This is great. I also hit 1,000 followers on my Facebook page during the event. I am so happy. Thank you to everybody, and Dirtman here, bringing geology to you from the Montour Fossil Pit. We'll see you next time. The Dirtman Report is sponsored by APM Automotive, your trusted source in York County for all your automotive needs.
So there you go. I am now have some ads in my stuff too, just like Jerry. So back to you, Jerry.
Great job. Yeah, that was a great great video for sure. So we like to see more of your stuff here. So all right, we'll keep going here. I'm gonna back up here. Oops. All right. Continuing on here. Buttonwood Nature Center, home of the Institute, as it's now called, in Waynesboro. They are a supporting sponsor for us. Don't think Tracy has joined us again tonight to talk about Buttonwood quickly, but you can find them on Facebook. A brand new name announced actually early April. And we'll be talking about Buttonwood and some of their coming up activities as the summer goes on. So check them out, Facebook, or they do have a website. Youth Archaeology Week is coming up in just about a month, actually, and in Dillsburg area. So if you have any grandchildren, children who are going into age grades 6th, 7th, or 8th grade, they are eligible to sign up and be a part of this week. And it will be doing real archaeology on a homestead property between the Northern York Historical and Preservation Society, the York County History Center, and myself and some volunteers that are actually either in the room tonight or they have relations that will be doing archaeology with us. Red Lion Telescopes with Wade Kraut. Talked to Wade the other week. He said his telescope business is really doing quite well after the solar eclipse. So this is actually he works out of his home. You can go to his home and actually go into the living room to the showroom and see what telescopes he has available to purchase in the Red Lion area, or call him at 717-378-1422. And he'll be glad to talk to you and tell you what's best for what your interest is. Zoom Rock Room schedule coming up. Next time we get together, June the 4th. I'll be doing the geology of the vacation spots on the East Coast. If you have a favorite vacation spot, it doesn't have to be on the East Coast. Send it to me or give it to me in the chat room tonight, and I'll add you to the list. We'll talk a little bit about the geology of your favorite vacation spot. June 18th, Fossils of Pennsylvania. We're giving the college academic people kind of off the summer. July 2nd, we're trying to get a program by the owner of Coral Caverns in outside of Bedford. He did express interest in doing a Zoom room with us when we were out there with the bus trip 2 weeks ago. July 16th is going to be a vacation, our summer vacation break. I'll be in Schuylkill County actually doing a geology walk at a new county park called Frog Hollow. Very small property, but has some very unique geology. So more about that later too. August 16th, I'm going to talk about the meteorites found in Pennsylvania. And we may have a special guest joining me with that. And August the 20th, who is Atreus Weiner, is a local educator here in the New York area. But he had a fascinating hobby and actually set forth a big foundation for other people to work off of in local paleontology. So that's the schedule through August, and then we'll get back into September in school and try to get the college of faculties back involved with our Zoom rock rooms. Coming up, June 8th and 9th, Cador State Park in Hanover, Pennsylvania. It's their second annual Eco Experience Cador's Outdoors. Lots of activities. I believe it's $5 a person to get in. Saturday, June 8th, Sunday, June 9th. 11 to 6 on Saturday, 11 to 5 on Sunday. You pay the flat fee to get into the gate, and everything else except for your food is free. Rock climbing, they're going to have a planetarium set up there. We'll be doing a fossil dig again with new Ringgold material. Just lots of other activities going on. So stop by Cador State Park that weekend.
Yeah.
And even come down and camp out at the campground. All right. This is one of the things that happened in the last couple of weeks.
Decided she didn't want to know the difference between the brake and the gas.
This is a Eurypterad. You might remember Dean Rucchio did a program on Eurypterads earlier this spring, the high school student. And Dean came to see us when we had the bus trip out at New Paris Quarry in Bedford County. As I said 2 weeks ago, Dean came out because he had been starting to find some fragments of Eurypterads at New Paris. I think he said he's been there. He spent 30 hours at New Paris collecting so far. But anyway, he came out to find some more stuff. And after I met him and our group went up to the top of the quarry to fossil collect, Dean was down at the bottom of the quarry, and we heard this loud yell take place. And Dean found this almost complete Eurypterad, and it made his day. It made his trip driving from Philadelphia to New Paris worthwhile. And people that were on the bus trip that maybe got to meet Dean, you find out that he is a very educated person. I think very highly of him with his knowledge and his talents, and this kind of is a reward for him. So I'm happy to announce that he has found a complete Eurypterad at New Paris, first one ever, by the way, and he might be back on our show in the future for another program. So that's the end of the introduction tonight. We've been having some other fun in the last couple of weeks with lots of programs going on. Last week I said I felt I needed a Lear jet to get around to where I had to be going, what and when. So, but we survived in between the bus trip and doing programs in Schuylkill County and doing some programs around here, including an astronomy program Friday night. Where I had to do the program called "If You Could See, This Is What You Would See," because it was cloudy. So we had to entertain the 18 people with a classroom deal, and that went okay too. So anyway, great to see all 22 of you in here, minus Melanie and I. So I'm going to move on here because I know Dan's ready to go. So you might remember Dan Davis was with us a year and a half or so ago to do a program, and I always give credit where credit's kind of due. So Diana Geist gets the extra point for finding Dan Davis at Cherry Springs State Park a couple of summers ago when she was up doing astronomy, and Dan Davis was there also, and they got talking. And of course, Diana likes to use resources, so she mentioned the Zoom Rock Room to him and to me, and we got together. But anyway, Dan Davis is back tonight. He studied geology at Princeton University, did a PhD in Earth and Space Sciences at MIT, and worked as a postdoctoral fellow at Columbia University before joining the faculty at Stony Brook University, where he remained as a full-time faculty member until he retired in 2022. His areas of research cover a range of tectonic and geophysical problems, with a special focus on theoretical and laboratory studies related to the mechanics of plate collisions, and mountain building. And other areas of research include geological aspects of nuclear test ban monitoring and the application of geophysical techniques to Quaternary and Holocene geology. He's a lifelong amateur stargazer, and he co-authored the very popular astronomy book called Turn Left at Orion, which is now in its 5th English edition and is also available in Italian, Korean, and Chinese. So we welcome back Mr. Dan Davis, and I know I'm going to enjoy your program with the thrust faulting, the horizontal movements. It is going to be a moving program tonight, so
That's right.
it's all yours, Dan.
All right, thanks. Hi, everybody. Let me just make sure I've got the. Let's see. Everybody seeing this?
Yes, sir.
All right. So I was saying before, this is a picture of a younger me in a part of Pakistan that you can't go to safely. Well, it wasn't safe then either, but I wouldn't be stupid enough to try to go to now. And I was there working with a group that had been doing field work in Pakistan for a number of years. They brought me in because of some of my theoretical work on the physics of mountain belts and wanted to apply it to Pakistan. And I was particularly interested in joining them because in many ways, Pakistan is experiencing now what our part of the world experienced in the past. So I'm going to try to convince you that Pakistan is really relevant to the Northeast, particularly Pennsylvania. So my sort of starting question is, what was this thing called the paradox of overthrusting? And you know, what do I mean by thin-skinned mountain belts? So very briefly, I'll remind you of some of our region's convergent tectonic history. There's been a lot of plate convergence happening here. What do I mean by fold and thrust belts and accretionary prisms? Why they are really mechanically the same thing. What was this thing called the paradox of overthrusting, and what do both fluid pressure and this concept I'll talk to you about called critical taper, that is at the core of how we now understand thin-skinned mountain belts. What is that? How do you model these thin-skinned orogenic belts, and what do I mean by thin-skinned? And finally, why do you go to Pakistan to study Pennsylvania? So, you know, look in the, you know, at a rather distant past, and, you know, you guys are no doubt familiar with the fact that we have recorded in much of the Northeast the Grenville orogeny, which is very widespread. You know, you see it not just a whole bunch of places, and the one I'm most familiar with would be Adirondacks, but this was a major plate collision with undoubtedly having shallow fold and thrust belts involved, but those things are pretty much eroded away by now, so we don't really see them. There's obviously rifting later, and then the first of a series of events that caused collisions, plate collisions in our area. So the first of them was the tectonic arc coming in. You know, think about, in this case, there's currently a very active arc continent collision that my colleagues and I studied quite a bit, which is the Luzon arc that evolved with the Philippines, is actually colliding with Southeast Asia. And that collision is causing the rising up out of the sea of the island of Taiwan.
There you go.
So that is, not only is it an arc continent collision, but what's really relevant for us is it's not cookie cutter. When you look at schematic diagrams of plate margins, either extensional or contractional, to give the idea that things move in and out perpendicular to the margin. But most collisions are oblique. They're not perpendicular. You can't represent them just in 2D. So we had that oblique collision causing the tectonic orogeny. You guys are somewhere out here. Me in central eastern Pennsylvania, I'm not involved in that yet. I'm somewhere well offshore in Avalonia. And eventually there's some controversy about exactly which parts of which margins had subduction in what direction. But the bottom line is that this chunk of crust, which included a lot of places up into the maritime provinces of Canada and beyond, and also eastern Pennsylvania and Rhode Island and so on, that started to approach proto-North America. And the result was another non-cookie cutter oblique collision, the Acadian orogeny. And then sometime after that, the Big Show. When I tried to get people to visualize what this must be like, imagine in the future, some of the seas in Southeast Asia closing up, getting subduction. You'll have collisions of various islands into Southeast Asia. You know, Borneo comes in, for example, and parts of the Philippines. But then eventually Australia would collide. So you can think of these, that as being kind of like our history. Then you had these separate geological terrains coming in, and then the Big Show with collision of Africa. And what you'll see again and again here is you've got zones of compression, not just the basement rocks being brought up to the surface, not just magmatic intrusion, but you've got sedimentary rocks, often made of sediments that came off of highlands behind them, eroded rock, eroded basement rock, and those get shortened. There's collision. That's a recurring theme. In our case, you know, we go back to the Mesozoic rifting, and then here we are today. Okay, well, what we've seen then is different types of convergent plate boundaries. So think of where this might be. You know, if you flip it right, left, if you want to be looking north, in this case, you're looking south along the coast of South America. You would have the Andes with this thrusting to the east, but also offshore in those areas like Peru, parts of Peru and parts of Chile, where you have a decent supply of sediment coming in off the land, you build up a sedimentary wedge that actually turns to be two-sided. And we'll see a little later why it's two-sided. So you end up with a thin-skinned fold and thrust belt. Thin-skinned because the basement really isn't involved in the shortening. And also an accretionary prism, which is out here much closer to the subduction zone. Continent-continent collision. Well, before the continent actually arrives, say you go back 50 million years to the India-Asia collision, you still had subduction beneath Asia, and you had an accretionary prism there. As time went on, and the continental lithosphere came in and it's buoyant, doesn't want to go down, so you get this major plate boundary. So this might be Himalayas before you get the major uplift of Tibet. So over a century ago, Swiss geologists would look at places where you had, you know, river valleys that cut into the Alps, and they noticed really big scale folding. I dashed it in for you. Eventually the dashes will go away. But even between my dashes, you can see that there is serious folding going on here. So they realized that if you add up the shortening involved in each of these. Start like without folding, and then you create folds like these. You wind up with a lot of north-south shortening. Added up, there's got to be tens and tens of kilometers of horizontal displacement and shortening in the Alps, and that's not even counting the places where there are thrust faults with significant offset. So they looked at this and realized, okay, here's this folding of these layers, and it reminded them of tablecloths. So you take a tablecloth and you scrunch it, and the view from above might look like this picture. And there were French-speaking Swiss geologists, so they reminded them of nappe de table, or tablecloth. So these kinds of big folds came to be known as nappes. Closer to home, this is an outcrop I love in it's part of the small but really very interesting Mid-Hudson fold and thrust belt. That's not too far from Catskill, New York. And take a look at this. I'll ask you to take a good look at these rocks. I've drawn in some yellow lines here as a hint. Can you see? You can see sort of horizontal but wiggly layers. And in them, you see these vertical lines. That's space solution cleavage. So that is a mechanism that is pretty good at producing shortening. You got a lot of it in the Allegheny Plateau, but it works best. It's the really efficient one if you have fairly fine-grained rocks under compression for a long period of time, but not under so much stress that you get failure by faulting. And it can produce shortening by the stress concentration of grain against grain. You wind up dissolving away planes and you get shortening. Below that, I'm about to draw in, can you see, here's a pretty good set of folds, right? You see this folding, and that folding has got space solution cleavage in it as well. But I want you to look at that folding. Does it look symmetric? Can you see the folds leaning in one direction? Right? There's this fold. I don't know. Can people see my my arrow? Yes, I see some nodding heads.
Yep, it does.
You see this fold and that one there. They both seem to lean to the right. That suggests a sense of shear top to the right. And that sense of shear is known as vergence. And it's a very strong indicator of direction of motion. So when you look at these rocks up here, you say, okay, they're shortened by space solution cleavage. Some of them are obviously shortened by folding. And they're shortened in a way that has shear top to the right compared to what's below. But then look below this point. This is a formation called the Esopus Formation, and this is the Glenary. And you look down there, and if you look carefully, you see a little bit of space solution cleavage, but no folding. This stuff below is much less deformed. It's down to maybe 1 or 2% shortening, but this is down to many tens of percentage shortening. And what we have along this surface I've partly drawn in red is called a detachment, or it's very commonly known by its French term, décollement, which means ungluing. And it's literally where the rocks above are detached or unglued from the rocks below. And we know the sense of motion along this detachment fault is left to right. And in a mountain belt, the back end's called the hinterland and the front end's called the foreland. So this separates the shortened rocks above, which have moved. They're called allochthonous. They're the rocks that aren't where they belong. They started out somewhere well to the left. From the ones that are basically not shortened, the ones that are in place, the autochthonous rocks. Well, you see this in mountain belts all over the place. So sometimes you'll see diagrams that go left to right, sometimes right to left. Well, the basic point is you've got allochthonous moving rocks over autochthonous in place rocks. And there's a low angle thrust fault along a detachment or décollement that separates the two. So imagine you got this and then everything stops and millions of years later there's erosion. So let's erode into all of this. And what you have is places where you've eroded all the way through the allochthonous rocks. And you sort of have a window into the rocks below, the autochthonous rock. And that's known as a window, or more commonly in geology, a Fenster, the German word for window. Other places, though, you can have an isolated bit of the stuff above the detachment. And you look at this, you realize that's moved. You figure, how the hell did it move? What pushed it? Right? It's not attached to anything to push it. Well, you know, in the past, it was part of something that moved. But now it's isolated, and that's known as a Klippe, another German term. And it's probably the most famous Klippe in North America is the Chief Mountain Klippe out in right on the edge of Glacier National Park. This is yours truly pointing it out. My wife and I were driving from Glacier Park up into Canada, and I saw Chief Mountain, and I just had to pull over. It stands up. That's, you know, close to a mile of relief there. And you look at it up close, it separates Precambrian from Mesozoic rock, but they're in the wrong order. Like, normally, the Mesozoic rocks, of course, would be above the Precambrian rock. But what, of course, has happened is somewhere, way off to the side, Precambrian rocks have been thrust up and then over on an overthrust. So here we've got a detachment, a décollement, between the Precambrian and Mesozoic rocks, the autochthonous and the allochthonous rocks. So these rocks moved at a pretty low angle. So there was long-term questioning about how this could work. Now, so how does low angle, thin skin overthrusting work? And some people, physics-minded people, said, okay, let's do the problem. Let's take a block and say it's sitting, block of rock, and sitting on top of a detachment. What would it take to push it across the detachment? Well, it's fundamentally the same problem as having a box on the floor. And what does it take to push the box? It's really, you just got to push with a total amount of force equal to the weight of the box times the friction coefficient. It's a 100-pound box, and the floor has got a friction coefficient of 0.6. You got to push with 60 pounds. Fundamentally the same problem, and that works fine with a box. But what if you've got a box that's very long and weighs, you know, a ton? You can't push it, but you've got a tractor or something that could push it. The problem is you can't push it hard enough to make it move. Why not? Because if you started pushing it, you'd crumple the box. These arrows get bigger with depth because rocks get stronger with depth. For the same reason that if you pile a bunch of boxes on top of each other, the more boxes you have, the more, you know, force you need to push them. Well, the effective friction is that rocks are stronger with depth. So, but you can calculate all that, and you can work it out, and you find out, and this was almost 100 years ago, people did the math and they found that it doesn't work. you cannot move a block of rock over a typical geological surface. But, you know, all these Swiss geologists knew that they had places where there were rocks that were not where they belonged. They came from far to the south. The rocks below them do belong there. They knew that they had allochthonous rocks over autochthonous rocks. And they would bring it to their, you know, physics friends, and physics friends would just say, hey, this can't be true. To have been shoved here would have required too much force. The whole block of rocks would be crushed. And to sort of caricature this back and forth, this paradox of overthrusting, where you had geologists saying, look, we have evidence this clearly happened. And the physicists, the ancestors of today's geophysicists and tectonophysicists, would say, it just can't be true. The physics says it can't happen. And for the most part, the geologists really didn't fully understand the physicist argument, and the physicists didn't have the geological savvy to really understand the geological evidence. So their kind of response was, well, let's just ignore the problem. Pretend it's not there. But somehow they did move. So what do you do then? Well, people started redoing the problem, and they had a clever idea. Large-scale overthrusting does work if the thrust sheet slides downhill. All you need is for these overthrusts to go downhill, and gravity will help. And physicists say, yay, we solved it. And the geologists said, no, because they don't go downhill. If anything, they go uphill. The problem's even worse. So then there comes a series of a bit of thinking that is summarized by the most geological experiment possible. Take your stereotype of geologist. When I would be recruiting students and saying you should become geologists, you know, really smart students at Stony Brook who were looking for some place where they could apply their interest in math and physics and chemistry, I would say, yeah, I admit we're nerds, but we're the cool nerds. Okay? So take that stereotype of geologists, and you get the famous beer can experiment. A couple of geologists are sitting around upset about the paradox of overthrusting. You know, one of them's downing a beer. Because, you know, that's what geologists would do. And then they had a thought. You know what? Instead of throwing away this beer can, I'm going to put it in the freezer. And the other guy says, you know, I'm going to take out another beer, and I'm going to set up some chairs. But not only that, I'm going to remove the window pane. I'm going to take the glass out of the window. Okay. Between them, they've only had one can of beer, so they're not drunk. Why is he doing this? Well, what they do is they take the new can of beer and they put it on this pane of glass. And they realize that they tilt the pane of glass enough, the beer can will slide. But you've got to tilt it at a really big angle before it'll slide. So that's not very satisfactory. Not very satisfactory. But then they take the original can of beer out of the freezer and they put it on the glass upside down, so that the opening that the first geologist drank out of is down against the pane of glass. Why would you do this? Well, inside that beer can is cold air. That cold air and the beer can are now in a warm room, so that air wants to expand. As the air expands, it applies a pressure, an air pressure. Air is a kind of fluid, so we could call it a fluid pressure on the bottom of the, from the bottom of the beer can onto the glass. And what that winds up doing is it winds up supporting part of the weight of the beer can. making it possible for that beer can to slide much more easily. And they get so excited about their geological discovery that the rest is history, and they get a little too carried away. That is the famous beer can experiment. But it really comes down to this. If you got a block on a board, the block slips if the slope theta is big enough. When is that slope theta big enough? Well, it depends upon the friction coefficient mu. The bigger the friction coefficient between the block and what it's sliding on, the bigger that angle has to be. It's also true that if you take this from being tilted and make it horizontal, it's also true that the bigger the friction coefficient, the more force you have to use to move the block. But as the beer can experiment showed, fluid pressure can support part of the weight. That effectively reduces the friction coefficient and makes it easier to push something. So what if there's elevated fluid pressure? And the first part of the solution of the paradox of overthrusting came a long time ago. Great petroleum geologists, Hubbert and Ruby, realized that high fluid pressure in pore spaces could help out, just like with the beer can. Why would that happen? Well, if you've got pore spaces down near the bottom of an overthrust, and they're connected by pathways to the surface, then the pressure of the water in the pore spaces is going to be no more than the weight of a column of water to that depth. But if those pore spaces are isolated, they're bearing a lot of the weight of the rock. So you have higher pore fluid pressure, and that, like the air in that beer can that came out of the freezer, can help support the whole thing. And they had oil company data showing that in some cases there is elevated pore fluid pressure. So fold and thrust belts work. Overthrust work if the fluid pressure is sufficiently high. But unfortunately, when you do the math, it's usually not that high. So the paradox is partly explained that way, but not entirely. There's got to be more to the story. But take a look at these cross sections of mountain belt. Canadian Rockies, Southern Appalachians, Western Taiwan, from my colleague and mentor, John Suppy. And you notice something about all of them. They're tapered. They're skinnier at the front in the foreland than in the back. And that is a big clue. Let's think about what do these things look like in the inside. So here's a geological map here in the Sawtooth Range in Montana. And if you're used to looking at geological maps, you'll see, boy, there's a lot of thrust faults. And it seems like every time you get one of these thrust faults, just above it is this blue stuff. Okay, these carboniferous rocks again and again and again. So this is repeating. When you look at it in cross section, here's sea level. You see all these thrust faults, and you can see that these packets of material that were all once lined up are now stacked with an awful lot of shortening. And in each case, the same limestone winds up being brought up to the surface on the same shaly rock. So here we've got this place that clearly has a lot of folding, and it clearly has a lot of thrust faulting. And what those two things have in common is that they allow horizontal shortening. And a wedge-shaped mass, generally of sedimentary rock over an attachment with folding and thrusting, is of course called a fold and thrust belt. But a fold and thrust belt is basically like an accordion on a table. Start out with this accordion on the table and say pin the front end of it to the table and push it from the back. The accordion will shorten, right? But for the accordion to shorten, there has to be a detachment, an ungluing, a décollement between the accordion and the table. be a low angle thrust fault, if you will, between the shortened and moved accordion, the allotron, and the sitting there minding its own business autotron below. So this is actually a publicity photo taken at Princeton University a number of years well after I graduated. But I continued working with a couple of faculty members who I knew there. Tony Dahlem, one of the great geophysicists of the second half of the 20th century, and John Suppy, who's now one of the most renowned structural geologists in the world. And they got a bulldozer to push a bunch of soil. And lo and behold, that soil bulldozed up into a wedge shape. Nobody piled it up like this, did it artificially. That's what the bulldozer did. And that is the idea behind a critical bulldozer wedge. And what is that? Well, here's a picture of this thing, an accretionary prism or a folding thrust belt. And if you have snow pushing a snowplow, a bulldozer pushing soil, or plate tectonics pushing a folding thrust belt or accretionary wedge, it doesn't push it into a rectangle. It pushes it into a triangular shape. Now, why does it do that? It does that for reasons we'll be seeing. If you want to model this, there are basically three ways of doing it. One is paper and pencil. You do the physics, you do the boundary value problem, and you work out the state of stress inside. A second way, this is from something one of my students did. You do, say, a finite element model, and you put in different strengths of materials. Here, a shale and a salt and basement rocks and more ordinary sedimentary rocks, and you basically push it from behind, and you produce a shape. And the third, really the most fun, is analog or sandbox modeling. So let's take a look at what a sandbox model does. So you start out like this. This is a side view through a glass side plexiglass view into a model, sand model that has got layers in it. This rectangular shape, you can see it here, is a backstop. It's something rigid. You can think of the rigid backstop pushing to the right, or what's actually happening here is there's a mylar sheet pulling out underneath to the left. And look what happens. You produce thrust faults, okay? And then more. And over time, you produce more, and more, and more. And look what happens to the shape. They go into a wedge shape. If you do the theoretical boundary value problem on a piece of paper, or you do it analog model like this, or you do it on a computer, this is what you get. And that shape is called the critical taper. It's the shape that it reaches. And if you redo that math for places like at a subduction zone and accretionary wedge, you get a shape that you can predict. So why is it a wedge shape? Well, it starts out slightly wedgy. If you think about it, as you're getting a mountain belt is approaching, say, as the Appalachians are being thrust to the west, or Himalayas thrust to the south, they're weighing down the plate that they're going over. That causes flexure. So you get what's called a foreland basin, a basin in the foreland, and sediments coming off that's eroded off high altitude, it's deposited by rivers and fill that with sedimentary rock. So you're going to have some stratigraphic taper. But on top of that, it needs to attain what we call a critical taper. That's the minimum wedge taper for the thin skin origin to be pushed over its stake If it's thinner than that, it'll crumple in the back. How does rock crumple? By thrust faulting, fattening up until it reaches that taper. So, the material deforms until it gets to that shape, after which it slides stably. It continues to grow as additional material is encountered at the front. The critical taper is the shape for which the wedge is everywhere just on the verge of failure under horizontal compression, including at the basal décollement. That basic idea underlies how we understand the physics of these things being orogenic belts. So the wedge grows by adding new thrust sheets at its front. So here's thrust number one. Well, a little bit later, there's thrust number one, and two more thrusts are formed in front of it. Later, another one, and another, and another. So what happens here is, in an active folding thrust belt or cushinary wedge, the thrust at the front is the youngest one. The ones behind still have a little bit of movement to maintain that taper, but basically, we say geologically, they young to the front. And it reaches a critical taper, a wedge shape that you can calculate based upon the properties of the material. In this case, sand against sand and sand against the mylar and the base. That's going to be different for different geological settings. Somebody else is modeling here, this group, Yuvichi and colleagues, when they make a base with high friction coefficient, you get a fat wedge. Low coefficient, not only do you get a skinny wedge, but look what's different. Look which way all these thrust faults go. They dip towards the hinterland with the hanging wall on top moving towards the foreland. That's true at high or moderate friction, but if you've got low friction, look, a lot of them go backwards. Some dip one the normal way, others dip the other. What's going on here? Well, the best way to illustrate this is a very quick experiment I'll run through with you that I would always do with students. You take a bunch of sheets of sandpaper and duct tape them together in the back. You put that sandpaper in a drawer, in this case a sample drawer, and rain in some flour. You don't compress it, just make it very gently, make a layer of it, and then you put, in this case, some athletic field marker chalk in. Then some more flour and a different color marker chalk. And then you make a little football field hash mark, but instead of every 10 yards, it's every 10 centimeters. These will become strain indicators, and watch what happens when you push it. You build a wedge with thrust fault. And then you take, in this case, a transparency sheet and cut into it and look at the cross section. And in the cross section, you see a whole bunch of thrust faults. So can you see here the offset in this frontal thrust in the red layer? There's a thrust fault here, another there, another there, another there, and so on. And you can trace these thrust faults down below. And they all verge, they all have motion towards the foreland. And you see these marker dots, these hash marks have gotten close together, and there's really intense deformation at the surface. Well, what if instead you put in graphite and make it a weak base? Think salt, for example, for extremely high pore fluid pressure. And the hash marks don't get compressed together as much. The shortening is less. When you cut into it, you find it more complicated. They're not all going the same way. There are thrust faults that go backwards. And the taper is much narrower. You compare with weak décollement and strong décollement. So maybe in salt, because remember, salt may feel hard in your hands, but at very shallow depth, it's ductile, it flows over geological timescale. So salt, or extremely high pore pore fluid pressure will give you a very weak base and a very shallow mountain belt paper, and much less intense deformation of the surface. So we got the situation. Here's the hinterland and the foreland, and here's the décollement. Okay, if the motion is towards the foreland, so think of sort of the finger of God pushing this way. Well, unless for every force is an opposing force, otherwise you've got accelerations. So this is the direction of maximum compression, and we call that the sigma 1 direction. Well, if you take a rock sample and you squeeze it, it'll tend to fail at something like the typical internal properties of rock, something like 30 degrees off of sigma 1. So you can get a low angle dipping thrust fault going that way, or a steep one going that way, and they're both the same angle off of the compression direction. Well, which one is more preferred? Well, the lower dipping forward thrust ones are preferred for two reasons. One is it's closer to the weak planes of bedding, so you can cheat that way, but also to get the same amount of shortening, it doesn't have to fight gravity as much. Here, you're fighting gravity by going up more than necessary. So that's why forward dipping thrusts, shallow forward dipping thrusts, are preferred in most mountain belts. And if you have remember structural geology, this is basically a more Coulomb diagram expression of the fact that when you have a weak base, this angle gets very small. So if you have salt, then the compression direction is not tilted a lot, but it's nearly horizontal. What does that mean? It means that whereas in a normal mountain belt with a strong base, you have this preference for forward thrust. But if you've got a weak base, what's really happening here, you've turned off the friction. I call that God playing air hockey with a mountain belt. Okay, it doesn't really know which way is forward. The way a mountain belt knows which way is forward is by friction at its base. If you have a thick salt layer at the base that's very ductile, because it's a couple of kilometers deep, then there's almost no resistance. It's kind of like being on an air hockey table. So if you've got a weak base in salt, you expect a very little taper and very few thrusts that make it to the surface, and some that go one way and some that go the other. Well, that's where we come to this familiar part of the world. You look at this physiographic map of Pennsylvania. This is obviously the physiographic boundary here, and there's another one there. Let's turn this into down here is where you've got some older sedimentary rocks. You've also actually got some Precambrian. You've got intrusive rocks. And here you've got all those famous Pennsylvania plunging anticlines and synclines. And out here, look at how far you go without really changing the age of rocks. And the main places where you do is river valleys that in size. So here, there's very little topography. Switch to another type of geological map, and you realize we're looking at the Piedmont, the Valley and Ridge section, and then the Appalachian Plateau section, this whole area. But what is it that makes this boundary? What is it different about the geological history here versus there? Well, go back to the Silurian, when we were at all very, very low latitude, and there were inland seas, we could have a lot of evaporation, and you get the Salina Formation, the Silurian age salt. And look at the boundary of thick Silurian salt. This is something that a very famous Penn State geologist, Terry Engelder, and I worked on, published a bunch of papers on years ago. But basically what happens is out here, you are, you've turned off the friction at the base of the mountain belt. And if you overlay a very crude cross section, it basically turns out that's where you change the nature of the décollement. Instead of Ordovician age shells like the Martinsburg, you're up in the Silurian age salt. And once you're there, you get this familiar pattern of faults plus faults going one way or the other, just like we saw in the published models in that little flower experiment flower. That is how it works when you basically turn off friction at the base of a mountain belt. So if you're interested in a place that has thick salt in some areas that causes very different types of overthrusting, but also has more ordinary valley and ridge setting, that has had oblique conversion, but has all of this right now, the best place really in the world is to do that. Look at that, it's Pakistan. And this is, that's actually the edge of an Afghan refugee camp. We were at, this is quite close to the Afghan border. And those hills back there have got older Paleocene limestones over younger Eocene shells. So obviously this is an overthrust. Somewhere back there, those limestones, the older rocks, were thrust up and over. So this is an area where you have fairly more ordinary overthrusting. But then over in the salt range, you've got thrusting over salt. This is actually the very front. It's taken from an edge spot, kind of equivalent of there, looking along the front. This plane here is on the Indian plate. And this is the front of Asia, Asia moving about an inch a year. And I went to the front to take a picture, and this guy happened to wander in front into the picture, which I thought was wonderful. So he and I are standing on the Indian plate. That is the Asian plate overthrusting. And in there, right near there is the Akira salt mine. If anywhere you see Himalayan salt, almost certainly comes from this mine. Colleagues of mine and I visited there. Turns out when the mine was a lot smaller, Alexander the Great also visited this mine. And when you go deep into the mine, it goes so far into the mountains that the workers can't go out multiple times a day, and it's a Muslim country, so they made a makeshift mosque out of salt blocks. And the reason they're reddish colored is that there's some, it's obviously not pure salt, there's some tamari and so on. But I thought this was a particularly lovely picture deep in that mine. But this, where behind the salt range, this is a seismic section of what you see. That should look a lot like Western Pennsylvania. A lot of low topography with thrust faults that are blind. They don't make it to the surface. Some go one way, some go the other. Why is that? That's because of the physics of mountain belts. The paradox of overthrusting is solved by combination of high fluid pressure and taper, but everything changes when you have something like salt, which basically turns off friction at the base of the mountain range. So that's why I would argue you go to a place like Pakistan that is the result of complicated plate collisions. Originally, the Asia boundary was north of here. Afghanistan is made up of a bunch of terrains that got plastered together. But towards the end, the edge of the Asian plate was along this red line, the Shaman Fault. And the Katwas Basin is part of a late terrain to come in. So that terrain, T-R-A-N-E, was coming in very obliquely. You see, that's the plate direction motion. And there's still a lot of strike slip motion along the Shaman Fault. That's where it's a huge earthquakes occur. And it was in the Suleiman. We did a transect across the tribal regions in the Suleiman coming out here near Dergazi Khan. And we also study the seismicity of the area. And I don't know whether you're familiar with these beach balls, but basically these all, they represent the motions of seismic waves away from an earthquake as recorded around the world. And these all say thrust fault. But you notice that the orientation of the beach ball rotates, changes around this lobe of the Suleiman Mountain. That's part of this issue of the oblique convergence, which is why this place is so worth studying if what you're really interested is something a lot closer to home. So that's why I would say, and that's why, you know, in getting funding from NSF to do it, we would say that to really understand the tectonics of northeastern US, particularly Pennsylvania, in the past, you want to go to a place like Pakistan. Thanks a lot.
All right, anybody have any questions for Mr. Dan?
I like the demo with salt and the flour and the sand.
It's I would teach for many years. I taught structural geology, and that was always the lab that everybody looked forward to. I learned after the first year of doing it that cleaning up afterwards had to be part of the grading, because if you know, I would go to Costco to buy flour, and you know, I'd come out with 100+ pounds of flour, sometimes more. And the first year, you know, they'd say, "Oh, you doing a lot of baking?" And I say, "No, I'm doing analog modeling of fold and thrust faults." And I'd get this blank look. From then on, I just said, "Yeah, we're doing baking in a geology class." But the janitors really liked it if you cleaned up afterwards. But it's there's something wonderful about doing something that simple that you can then cut into and see the difference between different types of mountain belts out of nothing but, you know, flour, sandpaper, sometimes graphite, and athletic field marker chalk. It's you know, an elegant little experiment that people at other universities have now taken up because it's so easy to do and fun.
We have questions. What's causing the sodium chloride to form?
Ah, yes. So if you look at a plate reconstruction for the Silurian, this part of the world was very low latitude at the time. And if you think about, excuse me, you know, right now, sea levels are moderately low because for two reasons. One, we've got a lot of ice locked up in Greenland and especially Antarctica, but also there's not an exceptionally large number of mid-ocean ridges. When you have more length of mid-ocean ridge, you've got more hot areas in mid-ocean, and that actually winds up displacing water. It's space where the ocean is shallower than it would otherwise be. The Silurian happened to have slightly more than average amount of mid-ocean ridge displacing water, and it was kind of deficient in, it didn't have an Antarctica loaded with ice. So sea levels were quite high. And when you have large inland continental seas at low latitude, it's a great recipe for evaporite deposits. And so we got very, very thick Silurian salts in the western parts of Pennsylvania, parts of western New York, and eastmost Ohio, and sort of northern West Virginia.
Greg wants to know, is there anything else than salt that can act as a slip sheet?
Great question. Yes. And what really does it, interestingly, is if you have a certain type of, you have a stratigraphy so that you have low permeability sedimentary rocks, fairly low in the section, but you also have a high depositional rate or high rate of thrusting. So you have pore spaces in the rocks below that are feeling more and more pressure because of thrust sheets going over them or sedimentation. What then happens is that the pore pressure can get so high that it's like 95 to 96%. It's high as the weight of the column of rock or sediment above. And there's some accretionary prisms in particular where that happens. The Makran, another reason for studying Pakistan, the big parts of the Makran in running off south of Iran is like that. So extreme high pore fluid pressures can do that. And that's what Hubbert and Ruby said a long time ago as the solution to the paradox. But it turns out that in most cases, the pore fluid pressure isn't that high. But yes, the other way it can happen is if you have anything else besides salt that goes ductile at depth. And halite is the only really common mineral that produces really thick deposits on Earth that goes ductile, has a brittle ductile transition at a very shallow depth. But if you get a big enough mountain belt, it could be thick enough so that even more ordinary materials can start to go ductile. And that's what we think happened in the Suleiman Range, which is why we did transect across the Suleiman, because that is so enormously thick that some of particularly tight fine-grained limestones can actually go ductile at depths of 12 plus kilometers. And that's why in this picture, in the I don't know whether you still probably don't see it, but in my opening picture with me and a Pakistani geologist, we were looking at that fold because we're interested in any exhumed limestones to see what kind of temperatures they got to see, whether they would have been close to weak enough to help weaken the base of the mountain belt. In that case of the fold, since it was a chevron fold, that means it's much more brittle, much less ductile. So that particular case it didn't. But yeah, you're right. There are other cases, and that's even before you get to other planets where it might get interesting.
Dwayne wants to know, when were you in Pakistan?
Oh, I've been in Pakistan in it was, believe me, it was before 9/11. And we're, the whole project, which was centered actually around Oregon State University. And I was sort of brought in as sort of a theoretical person on it. That whole project really just fizzled after 2001 because it was just not viable to go back there. So it was really the 90s when that group stopped going.
Okay.
I don't expect to get back there again, although they have this wonderful, for a geologist standpoint, history of really bad land management, which means very little sedimentary cover and really good exposure. of outcrops. Not good for them, but good for geology.
Anybody else have any other questions? Got some comments that the graphics were really great and much appreciated, and a great program.
Good. I'm glad you enjoyed it.
I see some.
It's really fascinating. You know, I've been very fortunate in that early on in my career, you know, I was of the generation of geologists that came in right after plate tectonics. I know personally most of the people who were the main figures in nailing down plate tectonics, and I published with several of them. But I was, you know, the young guy with that. So after plate tectonics, there was a lot of low-hanging fruit, a lot of big questions that could suddenly be addressed because of plate tectonics concept. So it's been a lot of fun for me because getting involved in the whole issue of thin skin tectonics allowed me to do a lot of really fun geological travel as well as theoretical modeling.
Very cool. Okay. Thank you, Dan, for joining us again tonight. Great program as usual. And Greg, I did hear back from Layer Architect. They did say that the email is stated is the same. layerarchitect@yahoo.com. So our address is right. Hey, Melanie.
Yes, sir.
You know what is so great about the country of Switzerland?
What?
The flag is a big plus.
That's a good one.
I thought that joke was kind of cheesy, but
Oh, for Pete's sake. I have a competitor in the room. Hey, did you hear about the snail that was going to be in a car race? So he put he painted a big S on the side of his car. That way, when his car went past the crowd, the people would say, "Look at that S cargo."
Oh, Terry, that's terrible.
I thought it was myself too. Yes.
I see some thumbs down in the Zoom room.
Numbers
Some
are going.
giggles, some chuckles, some shaking of the heads.
Yeah, but the room attendance is going down. Do you notice that?
yeah.
All right.
A groan in the chat.
We got it all. It was a fun night. And we'll be back in a couple of weeks into June. And everybody do have a great Memorial Day weekend. Whatever you're going to be doing, doing a little vacation trip, you're doing some camping, picnicking, swimming, whatever. Just always be careful. And remember, by the way, the programs are always videoed, and they will be on they'll be on YouTube. This will be on YouTube in a matter of a couple of hours. And all of our episodes, most of our episodes are actually on YouTube or on jonesgeo.com, our website. So with that, I'm going to let Mel take us out of here. So
Absolutely. As always, we appreciate all of your smiling faces with us, even putting up with some silly jokes, and hopefully learning something new at the same time. So we appreciate you guys joining us every other week. Like Jerry said, have a great Memorial Day, and we will see you all next time.
Bye-bye, everybody.
we'll
Thanks
see ya.
again, Dan.
Bye.
Thanks, Dan.